Hello, welcome back to another Science 10 video. Today we're going to continue taking a look at energy transfer within our biosphere. Our previous video has taken a look at energy transfer on a global scale through convection and due to the Coriolis effect, creating currents within the atmosphere, wind, and currents within our water. So on a global scale, there are trends we could look at. This video will take a closer look at specifically how water impacts our temperature on a local scale. Okay, well, what do I mean? Well, here is an example. Okay, water on an area's climate. So here is 4 cities in Canada. We have Victoria, Edmonton, Regina, and Winnipeg. Okay, if we look at the map, I circled them. They are around the same latitude. So in terms of convection and Coriolis effect, the wind and the temperature should stay about the same, right? The amount of hot air rising and cold air falling, because we're around the same latitude, temperature should be very close. Well, let's take a look. This is the measured results of a typical early winter or late fall. Edmonton -14, Regina -16, Winnipeg -18. Those three temperatures fairly close to each other. Okay, not too surprised. And Victoria is +3. Why is that? One of them does not belong, right? One of them does not belong. Why do you think that's the case, right? Why is that? Why is Winnipeg, Regina, and Edmonton fairly cold, minus, while Victoria can still remain positive? Okay, well, what's the difference between these 3 cities that are cold and the one that's different? Probably has something to do with that water. Okay, so why does water have that impact? That brings us to a concept we're going to look at called specific heat capacity. Okay, so what is it? Well, specific heat capacity basically is saying, well, the amount of energy it needs to absorb to increase temperature. Different object require different temperature, as you might have noticed. By definition, formal definition in science is the specific heat capacity. We use the little c, okay, or we may say big C, okay, in chemistry. But usually in here we're going to use little c. It's a substance. It's the amount of energy required. Here's the key: 1 gram, not kilogram, even though kilogram is the base unit. So 1/1000th of a kilogram, if you want. 1 gram of substance by 1 degree Celsius. 1 degree Celsius. In Chemistry 20, you'll learn a new way of measuring temperature called Kelvin, but Kelvin and Celsius actually the same unit, sort of. You'll learn about that in the 20 level. We'll not talk about here, but basically 1 gram of substance by 1 unit temperature. Okay, by 1 unit temperature. So for specific heat capacity of water, it's 4.19 joules per each gram for 1 gram Celsius increase. Okay, it's gram times Celsius because one substance by, right? 1 gram by 1 Celsius, 1 times 1. So each joules for 1 gram by 1 degree. Okay, so it's joules gram Celsius. Okay, multiplied by. Okay, a common thing is, well, I don't have air here, but our common thing to think about is aluminium. Okay, aluminium. If you take aluminium foil, think about how much it takes for it to warm up. Okay, does take a little while. Put your hand on it, but that is still only 0.897 joules per gram degree Celsius. 4.19 joules. Okay, to increase the temperature of 1 gram, only 1 gram of water for 1 Celsius. That is a huge number compared to most things we experience, which means it takes a lot of energy to raise the temperature of water even just by 1 degree. Therefore, regions, right? I think it explains itself. Regions near water tends to stay longer. Okay, tends to stay warm longer, while those who have less water heats and cools more rapidly. Okay, the temperature near the water stays more consistent. Remember, it goes both ways. If it takes a lot of energy to raise temperature, it has to lose a lot of energy to cool as well. It goes both ways. Therefore, those near waters, even in the same latitude, temperature tends to be more consistent. While those have less water, temperature changes much more rapidly. Heat and cool, there's usually a big difference between summer and winter months. All right. Now, the capacity to water absorb thermal energy has a great effect on our climate, as you just looked at. Okay. Usually substance in the lithosphere, in solids, in the ground, have a lower specific heat capacity than water, which means they cool and warm more rapidly, right? Victoria is warmer because it's near the ocean, a very large body of water, a very large body of water that stores those heat. And won't easily release those heat. So Victoria temperature won't change as much throughout the year like Edmonton. Now, talking about specific heat capacity, since we have numbers, we can actually calculate energy required for specific substance to actually change temperature. So we have to have a few definitions. First, the letter Q. Okay, Q is the quantity of thermal energy. The formula to calculate Q, the amount of energy for an object to change temperature, is that it's very easy. Okay, and think about specific heat capacity, right? It's 1 gram per temperature. So all you need to do is Q is the mass times, right? Q is thermal energy, mass times mass of the object. So 1 gram, how many grams there are? Be careful. Here we use grams. Okay, here we use grams. Okay, and the wait, what's going on? Oh, there we go. C, as it's discussed before, is the specific heat capacity in joules per gram Celsius, joules per gram degree Celsius. And finally, T, changing capital T. Sometimes I will try to avoid using little t because we have studied that for time in physics. We'll use big T for temperature. So change in big temperature, and the change is still the same. It's a temperature final minus temperature initial. Okay, temperature final minus temperature initial. Okay, the only big thing you probably want to pay attention to once again is mass is not measured in kilograms here, but it's measured in grams. So that's probably something you want to watch out for because we have spent some time working on as kilograms. So here is a sample question. Okay, we'll do 2 of them together, and then 2 you will try on your own. So calculate the amount of energy for 250 grams, conveniently converted already. 250 grams of water will release, okay, when it cools from 80 degrees Celsius to 20 degrees Celsius, okay? Knowing the specific heat capacity of water is 4.19 joules grams Celsius. So let's start. Well, list our variables. We're looking for Q, right? We're asking how much energy it needs to release. That's amount of energy. Okay, amount of energy change. Mass, 250 grams. Remember, I have to use grams here. Specific heat capacity, 4.19. Change in temperature is from 80 to 20. I would actually write T final minus T initial. So it's actually 20 degrees Celsius minus 80 degrees Celsius. Okay, this might be a bit, some setup might make more sense for some of you. The reason I'm flipping it around because I already count for the question it's released. Okay, it's already released, so you keep the number positive. But if we do that, so this one would be equal to, of course, negative 60.0 degrees Celsius. Why be afraid of negative number? So if we multiply them out, be careful, remember it's negative. So our final answer is negative 6.29 times 10 to the 4 joules. You might ask, hey, but energy can't be negative. Yes, energy can be negative, but change energy can. Work can be negative, right? In this case, it's not quite work because work talk about something different. It's just energy released. If it's negative, means energy is released. Positive means energy is absorbed. Since our question already asked energy released, so our answer would be energy released. I meant to say energy released is, hide the answer, is no sign. Released is already negative, right? Just like vectors, you do not have to say negative, negative. So released is already negative, is 6.29 times 10 to the 4 joules. Okay, so hopefully we're comfortable working with negative numbers from the physics unit. Okay, from the physics unit, and we're able to work with negative Q here. What does it mean? Negative means released, positive means absorbed. Okay, let's do another one. Pause the video and try it yourself. Determine the final temperature. A little bit different. We're looking for a final temperature. Determine the final temperature of a 500 gram of water if you were to add, add 9.00 kilojoules, 1,000 joules. Assume the initial temperature is 20 degrees Celsius. Okay, room temperature. This is what we usually consider room temperature. Or the standard temperature at 1 STMB, but we'll talk that it's for a next level. Okay, for the next level. But so Celsius. Okay, pause the video so you can try it yourself. All right, hopefully you actually try it yourself. So we do the same thing, of course. We're gonna make our list of variables. Okay, I use little t here. Maybe on your own paper you want to change the big T, just so you do not confuse get confused with time, especially if later on both are involved. Q is 9.00 kilojoules, so it's 9,000 joules. Do not worry about sig dig until the end. Okay, just keep track of it. All right. So mass is 500 grams. Conveniently, units is already correct, and specific heat capacity is 4.19 still. When the initial temperature is 20, what is the final temperature? All right. Step 2, use our formula, Fc delta T, but TF is not in there yet, so we should write our formula out. Now we rearrange the formula for TF, divide by MC first, order of operation. Do not break the brackets first. When we divide by TM, then we break the brackets by adding the TI. Be careful. Okay, when we do that, there's technically a bracket here when we type into your calculator. Be careful. Once we do that, okay, do the calculation, substitute. I got an answer of 24.2 degrees Celsius. So that is TF. Remember to go in and actually change the T's for your notes. Okay, I'm using a older version of the notes, so I didn't change all the T's. But once again, I do make a recommendation, change little t's to big T's. It's not a big deal. It's just a good idea so you do not confuse time and temperature. All right. So the second example, how you can calculate. There are 2 more we're going to look at, but I would like you to try yourself. Okay. Third question. If you add 3.57 kilojoules of energy, temperature changed, you know the mass is 1.51 kilogram. It is not water, okay, a substance. Be careful, not water. This answer is not 4.19. Determine heat capacity, okay? Spoilers, answer is 0.236. Okay, with correct sig of course. Okay, I'm gonna hide it. I look at longer. Try it yourself. Once again, try it yourself. The notes version will not have the answer. Will only have the answer posted without the steps. And the last one, before we give you the last example, okay, it's just a little bit, more. Specific heat capacity. Specific. This is really hard to say. The SHC. Now it's even worse. The specific heat capacity of a substance is determined using something called a calorimeter. Okay, we do not just know them from some kind of a knowledge transfer. We actually figure them out. Any device to use to measure quantity of thermal energy is called a calorimeter. Okay, you actually be doing experiments with calorimeter at the 20 level, chemistry 20. In here, we're not going to do an experiment with it, but I can tell you the basic concept. It looks something like this. There is a chamber inside where you'll basically heat up an object, right? Heat up an object, and as the object gets heat up, it's going to absorb or release energy into the water surroundings here, okay? As temperature is released or absorbed, all right, the temperature of the water is going to change. Water is 4.19. We have already measured that and determined that, okay? So from the change in temperature of water, we can calculate the change in energy within the water. Now, like I mentioned, right? The energy released can be detected as a change in temperature inside the calorimeter. Usually it's water, okay? Usually it's water. Now, heat gained by the substance is equal heat lost in the water, right? Heat gain, well, and vice versa. So that's why I didn't say which one is which. Heat gain is heat lost. Why is that? Which law of thermodynamics guarantees that is the case? Think about it, okay? Now, in the context, there's a bigger law that governs this, but in the specific case, we actually have a rule. It's called the principle of heat transfer, which means the energy to heat up and cool is taken from the surroundings, okay? It's just a special example of one of the laws we studied in physics, right? It's only a special example. If you remember, it's which law is it? Okay, it's law of something with T in it. Okay, think about it. Of. Okay, I don't want to review because I think it's a good moment for us to review. Okay, special example of what? So we can use, now we talked about the calorimeter, heat gained of a substance is equal to heat lost of its surroundings and vice versa. So we can do a calorimeter question. A 450 gram solid is heated to a temperature of 90 degrees. Okay, you place a solid into a calorimeter, okay, that contains 250 grams of water, okay, and has an initial temperature of 20 degrees. All right. Once the solid is placed into the calorimeter, the temperature of the vessel goes up 38.6 degrees. Okay, 38.6. Remember, was 20 degrees. Okay, was 20 degrees. It went up to 38.6 degrees. Determine amount of energy the water absorbed. This is a very straightforward question. You should be able to know. And determine the amount of energy the solid has to lose. Okay, because now one thing I want to take note, because the vessel goes up to 38.6 degrees Celsius, that's temperature for the entire substance. So the substance, just to help you, went from 90 degrees to 38.6 degrees. It will cool down, right? And the water in the calorimeter, right, went from 20 up to 38.6 degrees Celsius. This we can calculate. That's A. If we know this, I'll give you a hint. You will know that. And once you know that, so you know the Q for water, Q water, Q water, the amount of energy gained is equal to the amount of energy lost. Okay, telling you how to do this question. Now, if you know the Q and the temperature change, you can calculate C using Q substance is equal to mass of the substance, specific heat capacity times change in temperature of the substance. Okay, so Q water, you know how to calculate. Q substance, how calorimeter works. And finally, the amount of energy combined with the information, you calculate the specific heat capacity of the solid. I would ask you to try this question out yourselves. Okay, try this question out yourselves. If you want, the answer to ABC is 1.95 times 10 to the 4 joules, 1.95 times 10 to the 4 joules, and specific heat capacity is 0.842 joules per gram degree Celsius. Okay, so these are how you can calculate the amount of energy required to heat and cool a substance using specific heat capacities. Okay, and because water has such a high specific heat capacity, it keeps its surrounding regions warm. Well, I shouldn't say warm, but relatively consistent temperature. While if you have less water in drier areas, temperature varies much bigger. It heats up and cools down very much. So that's why Edmonton has really warm summer and really cold winter, while temperature in BC and even in East Coast tends to be relatively more consistent throughout the years. Okay, but there is still a little bit difference between East Coast and West Coast. Why do you think that happens? I'll leave that as a little conundrum for you to think about. Okay, and that wraps up our look at specific heat capacity and how water impacts the climate. But I know some of you may be thinking, water doesn't just change temperature, though, right? Water doesn't just change temperature and stay liquid. During the cold of winter, it actually gets really cold. It actually forms snow and ice. It freezes. Water also evaporates constantly, right? Water freezes. Water doesn't just change temperature. It changes state. Okay, it changes state. It changes state much more often in the polar regions than near the equator. Does that have an impact on our climate? The answer is yes. Okay, changing state of water is necessary for the water cycle. So that also contributes to the energy flow of through our biosphere, specifically the hydrosphere. So our next video will take a look at the energy required for water to change state. And with that, thank you for watching this video on specific heat capacity. Till next time, we'll take a look at state changing.